So I'm going to be starting with the atomic models and how they began. So John Dalton pretty much started this with how elements exist as discrete packets of matter, and in the 1870s scientists began using cathode rays, which were tubes with electrodes at each end emitting different lights with electrical current passing through them, and they called them cathode rays due to the charges or cathodes within them. And Eugene Goldstein was next, and he pretty much discovered that there must also be a positive charge in matter, not only negative, because when using a cathode ray, he discovered that they did not travel just one way, they traveled both ways. And J.J. Thomson was next, and he pretty much estimated the mass of the ray through how much they bent through magnets, the attraction of the magnets, and he discovered that they were not only rays, but tiny negatively charged particles called electrons. And he didn't really know the shape, but he knew that they were negative and positively charged, and knew the overall atom had a balanced charge. And negative electrons must also be arranged randomly in the positively charged matrix, and all this led him to creating the plum pudding models that are shown here. And Ernest Rutherford also found that the atom is mostly made of empty space, and in the very center there's the nucleus. And he found this through the gold foil experiment, and within this he used protons and passed them through a zinc sulfide covered screen, and some of the particles that would pass through fully, and then some would bounce all the way back towards him. And Niels Bohr was next with the Bohr model, and he gave us a definite shape of the atom and the different clouds that the nucleus has traveled in. And Werner Heisenberg came next behind him, and he pretty much showed that it was impossible to determine the speed and position of an electron both at the same time, which gave us the quantum theory model next, and this was because the electrons placed were on probability and not exact locations. So due to this, we began drawing them on clouds called orbitals, and this gave us the quantum mechanical model. So pretty much the orbitals that he was talking about were the S, the P, the D, and the F, and the electrons travel kind of in these clouds here, and they're just kind of randomly in there and not fully in like certain shapes. And the electrons that were given, where we describe them in exact positions through the principal quantum number, the angular momentum quantum number, and the magnetic quantum number, and also the spin quantum number, and these just give us the size, the shape, the orientation, and the spin. So now we're talking about the electron configurations, and with these we are given the S, the D, the P, and the F orbitals to work with. And when filling these, we fill them from left to right, just like we're reading or writing on a page. And we fill them with one valence electron first, and then we go back and we fill them with the second one. And it's always one pointing up and one pointing down because of the clockwise and counterclockwise rotations. And that's also why we can only give each one 2. And now we're on the mass spectrometry. And this deals with the isotopes. And isotopes are the same elements but different masses, and they can calculate altogether the average atomic mass. And with spectroscopy, it's the study of interaction of electromagnetic radiation with matter, and this is pretty much the experiment with the analyte. And the spectrometry is the use of the spectroscopy as a quantitative tool, and you're just pretty much drawing conclusions from the data from the spectroscopy. So in our mass spectrometry graphs, we over on this side are given the relative abundance, and down here the atomic weight. And whenever we have the highest peak on the graph, that's called the base peak. And all through the different types that are given to us with the different weights, they can tell us different things about the different parts of the element and how they relate to one another. And when trying to calculate the average atomic mass, you can use this equation down here. So now we're going to light, and light is pretty much just the different wavelengths in our lives. And we have the gamma rays all the way through the AM wavelengths, and usually we deal mostly with the visible light, which is just the combination of all the white light that creates the colors that we see in our lives. And each color, like shown here in the visible light, is just like every other one, given different wavelengths for the own color. And each wavelength are like different particles that make up the wave, and the waves are consistent with their wavelength and the frequency. And the frequency is just pretty much the time that the wave passes for a certain point in time. And all these here are pretty much just equations that you can use for different things and the different meanings for each one. So now we're at the 2007 AP question, and this is pretty much just calculating the percent abundance of each isotope, which is just the equation that I gave you earlier. and this is calculating the number of atoms in the sample given. So you just use your grams to the molar conversion to the percent abundance that we found in the first part to the Avogadro's number to find the atoms. And to find the wavelength in nanometers, you just use one of the equations I gave you previously, and you use what is given to you in the problem here, and you convert it to nanometers. And for this one, to find how much energy in joules, you just use another equation that I previously gave you right here. And so for this equation, this problem here, you're just trying to find if the photon has enough energy to break the bond. So you're just using the joules that you got per photon that you got in the previous one, and using Avogadro's number, and then you're converting it to kilojoules. And since that one is larger here than the 387 given, the bond can be broken. Thank you.